Welcome to lesson 24. Today we are going to start solving exponential equations, and we've just been talking about logs and log properties and so forth. Well, in this particular lesson I decided to split up, and in this lesson we will just talk about solving exponential equations. Then the next one we'll talk about solving log equations and continue on with some of our work with logarithms. But we're going to need our logs here as well. Okay, now to start out with, we've got some very good reasons why we'd want to solve exponential equations. How much money do we need to put in if it's going to earn 8% compounded quarterly? You know, this looks like that compound interest we talked about. And remember, to find out how much you have in the account, it's going to be your beginning amount times 1 plus, I like to say, your periodic rate raised to the number of periods. Okay, that's how you compute compound interest. Now, I know that's not what's in the textbook, but that's what's in my head. Okay, so let's see here. We want to have 500,000. So that would be this part. And it's 8% compounded quarterly. Now, quarterly is 4 times a year, so the periodic rate would be, what, 0.02? 2%? 8 divided by 4. And how many interest periods over 20 years if they're paying me interest quarterly? That guy's going to be 80. Okay, so when I put all this information into my formula, you see that I've got all of that. And look at where your unknown is. Because you know in algebra, it's all about where is that unknown and how do I get him by himself. Well, you might notice that if I can figure out what this mess is equal to, 1.02 raised to the 80th power, all I need to do is divide that off. Now, I went ahead and pre-worked these because I don't want to stand here and punch buttons on a calculator. You might want to get your calculator out and work through it as I do and see if you're getting the same result. So I'm going to take, and in fact, this is the safest way to put that into your calculator. Sometimes I have students that round things off because they'll do a part of the problem and just round it. If you're not careful with numbers this big, you can have some serious accuracy problems on that. And we come up with $102,000. Wow. So if you want $500,000 in 20 years and you're only going to get 8%, you've got to put in over $100,000 to start with. Now, I ask the question, is this sensible? 100,000 becoming $500,000 in 20 years? Well, I said, think of the rule of 72. That one day towards the end of class, I talked about the rule of 72, where you take 72 and divide it by your annual interest rate, which is 8%. Well, 72 divided by 8 is 9. So this means that approximately every 9 years, our money will double. So let's check this out. We've got about 102,000 now. So in 9 years, we would have, what, about 204,000. And in 18, another 9, it's going to double again. We're up to about 408. And, well, actually, 18 is as far as I need to go. We're at 400,000 now, and in those other 2 years, because of that whole snowball effect, yeah, it's at least reasonable. Okay? Well, we're going to change this a little bit. We're going to put in $4,000. So that would be our A naught. He's going to be 4,000 right here. We want it to become $500,000. Doesn't that just sound better than 500,000? I know 500,000 still sounds like a lot, but 500,000 sounds better. And we're going to have quarterly. We're going to leave it in there for 40 years. So 40 years, how many periods? That would be what, 160 periods? Okay. And we don't know the rate. That's the question we need to find. Now, I did go ahead just to be safe, and I said I'm going to let R be my annual rate because you know that this part is my periodic rate. And since it's quarterly, I'm going to take that annual rate divided by 4. And I know that looks very formulaic, but I think it's a safer way to look at it. Well, you know it makes sense. I have to find out what that R is. So you take the outermost, it's kind of like the edge of the herd. You're going to start picking it off. I know that's not so mean, but oh well. I need to pick off that 4,000 because he's on the outside edge, and that gives me 125 is equal to all of this to the 160th power. So what the heck do you do with a 1/60th power? Because right now, that's on the outside of the herd. That's what's got to be removed. Well, we do that by taking a 160th root. Now, you may have a key on your calculator. The xth root of n or whatever it might happen to be, you might be able to use that. And if you can't or you're having trouble using that, you'll notice that I also said you can take 125 and run your caret for a power. Because remember, we've talked in the past, if this is the 160th root, that's what? Power. Well, the 1 divided by 160th power. So you could key it all into the calculator that way. And if you take the 160th root of 125, you get 1.0306, and I've rounded that off. Subtract the 1 away, and we get 0.0306, and then multiply by 4 to get up to an annual rate. And actually, I bet if we carried everything, we might have gotten 12.25%. So if you could find some investment that was paying 12.25%, your $4,000 could become $500,000 in 40 years. Okay, but that way we know. Now, so far, these haven't been terrible, okay, but we've been dealing with equations that had exponents in them. You deposit $10,000 in a stock fund, so my A0 will be 10,000. Annual return of 15%. How many years? So we're going to work with an annual compounding here until you get the 500,000. And of course, that's a huge assumption. We're going to maintain that 15% annual rate. Well, 500,000 is equal to 10,000 times, and you'll notice that I'm letting my t here, this exponent is a little bitty t. That's how many years, because this is my annual rate, okay? Well, the outside part that's going to be moved off first is that 10 grand, so we divide him off. Oh, yeah, okay, I forgot I removed something here. So I divide him off and I get 50 is equal to 1.15 raised to the t. So you look at that and you say, what's up with having that t sitting up in my exponent, you know? But that's where my unknown is sitting. And so you've got to figure out, well, how do I solve that when that unknown is up in the exponent? I don't like that. You know, if nothing else, if you really had to have this answer, you could sit and play with it and come up with a reasonable approximation. But let's actually find out how we deal with it. I can't take a t-th root because I don't know what t is. So what I need to do is figure out how to get that t down out of the exponent. Move an exponent down. When have we done that? We had an exponent and we move it down out of the exponent. Logarithms. Okay. So here's a thought. How about if I take the log function, and I might as well use base 10 because I've got keys for that on my calculator, and I take 50 and I put it into my base 10 log, and I put 1.15 raised to the teeth power. That's so funny, teeth power. I take 1.15 up to the t power and put that into the log. Since these two quantities are equal and the log function is a well-defined function, those values have to be equal to each other. It wouldn't make sense otherwise. And so now I've got this nice little log equation, and what's really helpful is that this t can come down in the front. Remember our log properties? So I get log of 50 is equal to t times log of 1.15. And you know what? This is some ugly number. You can grab your calculator and look at it. 10 to what power gives me 50? You know, it's something between 1 and 2. And 10 to what power gives me 1.15? That's between 0 and 1. They're ugly numbers. But then I could divide those ugly numbers. So t equals log of 50 divided by log of 1.15. Now, by the way, I went ahead and wrote it here real nice and pretty. Log of 50 over log of 1.15, and then I grabbed my calculator and I said, what is that approximately? And my calculator said, well, that guy is approximately equal to 27.99, or essentially 28 years. So at 15% annual return, my 10 grand will become $500,000 in basically 28 years. Now, something I do want to point out to you, well, I thought it was going to pop up there. Okay, doesn't want to. This is the exact value. I must have it set up in another screen. That's an exact value. If you're asked for an exact, that would be it. And this is my approximate answer. And one other thing I wanted to point out before I left this screen is that I used base 10 because base 10 is a key on my calculator, so it makes it kind of nice for working it all out. But you know, there's another key on my calculator, ln, right? So here's what I'd like you to take just a second and do, and we're not going to do this on a regular basis, but I have this 50 equals 1.15 to the t power. Put these guys both into the ln function. Now likewise, they have to be equal, because if I take equal quantities and put them into a particular function, unless that function is just nutty, which this guy isn't, I'm going to get the same answers out, all right? And so then I drop the t, and I get natural log of 50 is equal to t times natural log of 1.15. And if you've got your calculator handy, because I don't, and I'm not the one that needs convincing, run this. And if you properly put that into your calculator, I know what answer you're going to get. You're going to get 27.99 years. Okay? So you choose. You can work in LOGs or you can work in LNs. Okay? Now, for solving our exponential, there's two basic kinds of equations we run into. And what I want to do is first practice with this particular type, and we'll do several of those, and then we'll switch over to the other type. So, I look at this guy, and I see 8 to the x is equal to 2 to the x plus 6. Now, my grief is that as I carefully analyze what I see, this is frightening. The fact that I have the x's up in the exponent says, oh man, this is not a pre-algebra problem. Now what some people do is every time they see the variable up in the exponent, they say, let's haul out those logarithms. You know, hauling out the logarithms is like bringing the cannon in here because you'd like to kill the squirrel that keeps getting in your attic or something. Not that I advocate killing squirrels with cannons, but you really don't need that firepower. See, you can do this in a much easier way. You can recognize that 8 happens to be 2 to the third power. So this is 2 to the third raised to the x, and that equals 2 to the x plus 6. You know your properties of exponents. If you have a power to a power, you multiply them. So 2 to the 3x equals 2 to the x plus 6. And the only way these guys are going to be equal is if these two exponents are equal. So then I'm effectively going to pull those guys off and say, look, for my equation to be true, I know 3x must equal x plus 6. So 2x is 6, x is 3. And you can check it back there if you like, okay? That was a whole lot easier than pulling out the big old mess of logarithms. All right? So if you can find that you have like basis, boom, go for it. Like on this guy. And remember, in the previous lesson, I suggested that if you don't easily see powers on your own, you might want to have a sheet of paper where you've written out some powers. Because then when you start looking at this, you might say 25 and 125. Of course, you're kind of thinking 5s. And you might look down through your 5s and realize, yes, here's 5 squared, here's 5 to the third. I can get these guys to have like basis. And because my variable is sitting up in that exponent, I don't want to bring out the logs if I don't have to. So, this is 5 squared raised to the 2x plus 1. And this guy is 5 cubed raised to the x plus 3. Power raised to a power, multiply the exponents. That does mean I've got to distribute. So I have 4x plus 2. And over here, as I distribute that through, I'll have 3x plus 9. Now the exponential function is also this very well-defined one-to-one function. If these two answers are the same, those have to be the same. So 4x plus 2 must equal 3x plus 9, and x is 7 when we go through and solve it. Okay? And if you'd like, sometimes for your own comfort level, I suggest that you actually take those answers and work them back in. It may just kind of help you to see what's happening here a little bit better if you do that. Now, it's not something that I want you to always feel you have to do, but it may help your understanding. Okay? Well, the good news on this guy is I only have one x anywhere in the problem, and I could use logs, but that's really grotesque. I can't imagine he's going to give me a nice answer. But then you might realize, well, as grotesque as that is, this is a power of 3. And this is a power of 3. See, when you see that variable sitting up in the exponent, I want you to first consider, because it is our path of least resistance, I want you to first consider, can I get the bases to be the same? If you can, go that route. All right? So I know this guy is 3 squared raised to the x power. The 9 is the 3 squared, so it's a straight substitution. Now a cube root is, what, a 1/3 power? And what puts him down in the denominator? A negative. So we've got 3 raised to the negative 1/3. Okay. Well, if you're all right with that, these get multiplied. So I have 3 to the 2x is equal to 3 to the negative 1/3. 2x equals negative 1/3. I pull off those exponents because for those quantities to be equal, those exponents must be equal. And x is negative 1/6. Okay. Now this guy is really obvious that you have like bases because you're looking at them. E. They are the same bases. So you might real quickly say, wow, I know this guy immediately is e to the negative 2x, right? Because the negative is what put him down into the denominator. So if e to the x plus 4 is equal to e to the negative 2x, x plus 4 has to equal negative 2x. So 3x equals negative 4. X is negative 4/3. Ew. You know what? That's just kind of there. Let's take just a second and see if that does make any sense at all. It's not a hard one for us to check. If we put that negative 4/3 in here, we would have e raised to the 4 whole is what, 12/3? So negative 4/3 plus 4 is 8/3. Right? Does that equal 1 over e, and I'm supposed to take 2 times that, negative 8/3? And you look at that and say, yeah, okay. Those two are in fact equal. This is my correct answer. Okay? Well, then you run into 2 to the x is equal to 7. And you say, all right, 37 is not a power of 2. And I've got that daggum variable sitting up in the exponent, which spells trouble. It says I have no choice but to pull out the big guns. I'm going to pull out the logarithm, okay? And I know that log is a well-defined function. So if I put in these equal quantities, I will get equal results out. Okay, with that in mind then, I get to use this property, which is the entire reason we bring out the logs. Because that x gets to be pulled down in the front as a multiplier. And so we get x times log of 2 is equal to log of 37. And as grotesque as those are, I just now have to divide. Okay? And in fact, here's what we come up with. Log of 37 over the log of 2. And you really should be running this in your calculator and see if you're coming up with the same answer. I came up with about 5.209. Now, by the way, it doesn't take much time to kind of double check that and see if it makes any sense. 2 raised to the 5.209, is that approximately equal to 37? Now, yeah, you can pull out the calculator and push the buttons, but what's 2 to the 5th? That's 32, right? So 2 to the 5th and a little bit more, I'm totally good with that answer. Okay? And this is where I put it. This is going to be your exact answer. If you are requested, and a lot of times on a course exam or on a final exam, we will say, solve this equation, give the answer as an exact answer. We might also ask for an approximation. And I want you to realize that if we're asking for exact, you've got to give it to us in this form. And then our approximation, of course, is once you run that stuff into the calculator and you're rounding it off. Okay? Last thing, remember, if I wanted to, and that's one of the reasons why I need to look at your papers and grade them carefully, you might choose to use natural logs. In which case, I would see your exact answer as natural log of 37 divided by natural log of 2, but I would still see the very same approximation of 5.209. Okay? Well, we've got another exponential equation, and of course the reason we're calling it that is I've got that variable sitting up in the exponent. That's the only location. I've got to get them down. Oh, but before I do, I have a little bit of a concern here, and that is this exponent is not applied to the 5. I don't want to start pulling out the logs just yet. You know what it would make sense to do first algebraically? You know, it always makes sense. Clean up before you get to work. Divide that 5 off first, and we get e to the 1 minus x is equal to, what, 310? You really need to divide that off first, because then I can go into logarithms. And you know what? With this guy being a base of e, I would rather use natural logs. You don't have to. You can use common logs, but I would rather use natural logs. And really, when you have to do a common log of e, I think you'll be happier going this way. Some of you might, well, I'm just actually going to run natural log of e to the 1 minus x is equal to natural log of 310. Now, why am I doing that? Because the logs allow me to bring this exponent down in front. Now, because that's a complicated one, I'm going to make him 1 minus x times natural log of e is equal to natural log of 310. Hey, and natural log of e is what? That's why I liked the natural logs here. So 1 minus x equals natural log of 310, and this becomes pretty easy to solve at this point. I asked my calculator, and it says, well, 1 minus natural log of 310, which is my exact answer, is approximately equal to negative 4.737. And of course, you can run that back in and see if this makes any sense in that situation. Okay? Oh, I was going to say, Amy, a really sweet student in class, said, well, she kind of looked at this a little differently because she said that from right here, she wanted to go with the definition of the logarithm. So she just used the basic definition that because I have a base e, the natural log of 310 has to equal this exponent. So she went right away to this statement by applying the definition. And if that's the way you'd like to go, that is a wonderful idea. Okay? Well, in this next guy, the bases are nice. We've got a 5 and a 3. We like those numbers, but we've got variables up there in each of the exponents. And my first thought is, can I get these to be like bases? No. No. All right, which means I have to pull out logarithms. What does it matter here? Would LOGs or LNs be more advantageous, one over the other? No. Whatever floats your boat. So you take LNs or you take LOGs, whatever you like. Because I think most students at this level prefer the LOGs, that's the one that I tend to write more often. Okay, and my whole reason in doing that is that then I can bring down those exponents as multipliers, and that certainly made one part of my job easier. X minus 1 times the log of 5 is equal to x times the log of 3. Okay. Now, problem is, I see an x here and an x here, and you know that my goal in solving is to get all the x's collected and then get the x by itself. Now, in order to do that, I think you can see I'm going to have to distribute over here on the left. So I will have x times log 5 minus log 5 equals x times log 3. Okay. Now it makes sense that since I have to get the x's collected, you want to grab anything with an x, bring it over here onto the left, and any term, so this guy has to come over to the left, and anybody that doesn't have an x needs to head over to the right side. Okay? Looks a little bit ugly, but we'll be fine. So we end up with x times log 5, and he's positive, so he's going to come over as subtraction, equals, he is subtraction, he needs to be added over log 5. Okay? Now, everything's hunky-dory, and believe it or not, these are, in essence, like terms, but it sure looks scary. So you might look at that and say, oh my goodness, what do I do to get the x by itself? Well, probably your best idea is to realize that it's a common factor and factor it out. X times log 5 minus log 3. Now take a second and look at that. If this gets distributed back, right? I'm right up to there. Okay. And you see the beauty of doing that is now with one move, I can get that x by itself. This is all multiplied on. I divide it all off. And I think I probably have that written down here. Oh, I was lazy and put ln's. It's less typing. I have log of 5 divided by, now where would I get 5 over 3? Oh, that log property, yeah, looky here. Subtraction of logs, I can say that's log of 5 divided by 3. Now, did I have to do that? No, you didn't have to do that, but it gives you a little bit less to key into your calculator maybe, gives you a little bit less chance of having inaccurate answers, okay? So here is one form of the exact answer, not the only form, and it's approximately equal to 3.15. Which, by the way, the fact that no matter which way we go, we should all come up with the same approximation is a very good reason to have those approximations, along with the fact that it makes it really nice to check it back in and see if it makes sense to the problem. Oh, one more. And this guy is going to take us a little bit of work, so I think I'll just go ahead and work it over on this board. All right, I start this guy out and I say, oh, crud, I've got the variable up in the exponent. And that wouldn't be a problem if I had like a 3 and a 9. But no, we've got a 7 and a 3. With a base of 7 and a base of 3, I'm not getting those puppies to be alike. It means haul out the big guns, we're using logarithms. Okay. Well, I'll use ln's this time. 7 to the 2x plus 1 is equal to ln of 3 to the x plus 2. Right? I am not multiplying logs on. What I'm doing is taking equal quantities and putting them into the log function. Okay? It's kind of like putting a quarter into the pop machine versus putting 2 dimes and a nickel into the pop machine. You're putting equal quantities into the function. The same thing should happen. Okay, these exponents now come down into the front because of the third log property that we worked on. So 2x plus 1 times natural log of 7 is equal to x plus 2 times natural log of 3. Now I have an x here and 1 over here, so that means I really am going to have to distribute this so that I can eventually start moving terms around. So I have 2x natural log of 7 plus natural log of 7. Do you see what I did here on the left-hand side? I distributed that quantity through the parentheses. And I'm going to do the same on the other side. Okay. Now, just like we did on the last problem, everything with an x needs to come over here to the left, and everything without an x needs to go over to the right. So this term I want to come over, and this term I want to go over to that side. Okay? So I end up with 2x natural log of 7 minus x times natural log of 3 is equal to 2 natural log of 3 minus natural log of 7. Huh. Okay? Now remember, I had to get all the x terms over here on the left-hand side so that I could get them together. And believe it or not, these are like terms. I'm going to factor out the x, though, in order to do the subtraction. And I have 2 natural log of 7 minus natural log of 3 is equal to 2 natural log of 3 minus natural log of 7. Now, I would like to go ahead in this case. Do you realize that I can combine these? I can condense them like in our last lesson. Okay? And by order of operations, this 2 has to go up first as an exponent. So I have x times natural log of 49 minus natural log of 3 equals, and here this 2 needs to go up. That multiplication needs to be dealt with before the subtraction. Order of operations is equal to natural log of 9 minus natural log of 7. Well, now I can condense based upon the subtraction. And if you're subtracting exponents, what was the operation being done? Well, that was division. Now those are some pretty ugly numbers, but sorry, I'm stuck with 9/7 and 49/3 because they don't come out evenly. However, the nice thing is I have x times this, granted ugly, but very acceptable numerical value. So x is going to be natural log of 9/7 divided by natural log of 49/3. Yeah, that's a lovely answer. Now, that would be my exact answer. Funny, when I did it in my office, I stayed in LOGs. Yeah, see, whatever you like. And I have the very same exact answer. Well, except I have a different base showing on my logs, but it is the same value. And I end up with 0.090. Boy, that's tiny. Okay? And you could double check that and see how you like it. All right, well, we've had some good practice here. And to recap, I said simplify first, simplify first. That means that if you get to this problem, and especially if you decide you want to use logarithms, don't jump in right away if you can do some simplification first. Number one, it's going to make things go much easier. And number two, less chance for error along the way. Okay? Because you wouldn't have to do the simplification, but seriously, you want to. Now, there are two methods that we talked about today in order to do your solutions when you see that variable up in the exponent. The first one you should consider is, can I get like bases? All right? And you want to think about positives and negatives and everything as far as, you know, maybe it's a 1/25, and that's 5 to the -2. Keep looking. Because if you can, that's going to be your easier way to solve. And if so, then once you get those bases equal, you can pull off those exponents because they have to be equal. And then it's an easy problem to solve. Now, if it's not possible to get your common bases, then what you need to do is take each side of the equation. These are equal quantities, and you're going to put them into the log function, and the results have to be equal. The reason for doing that is that then you can bring that exponent down in the front as a multiplier, okay? And then go through your solutions. These aren't that terribly hard, but to get some good proficiency, you really need to practice. So have fun doing some practice on that, and I'll see you in the next lesson.